All right, so today we'll start on the MOSFET part 2. For part 2, it is more on the AC analysis. Okay, for the AC analysis. So for the AC analysis, of course, we derive on the mid frequency. So for the mid frequency, if you still remember mid frequency, your objective is to draw the AC equivalent circuit and also to find the uh, Z in, Z out, AV, and AI. Okay, so basically we will go through again what we have done in BJT, but this one for MOSFET. Okay, it has three configuration. Okay, same like BJT. It has common source, common gate, and common drain. All right, so common source is closely similar to the common emitter, if you still remember. Common gate is closely similar to the common base, and common drain is closely similar to the common collector. Okay, and next is the when you have the at mid frequency, we also going to analyze at low and high frequency, but this one only for common source, same like BJT, only for common emitter. All right, so this is it shows for the AC equivalent circuit. Okay, if you still remember, in the common emitter you have hybrid pi model. Okay, hybrid pi model where you have R pi and then you have current source GMV pi. Then you start drawing your AC analysis. Okay, however, for MOSFET, you have this hybrid pi model also. It is also named as hybrid pi model where in BJT you have V pi. Okay, but in MOSFET you have VGS. Okay, VGS, and then current source is GM-VGS. Instead of you have GM-V-pi, you have GM-VGS. Okay. In BJT also, you have R0. Okay. If you still remember R0, but usually R0 is ignored because the voltage is too, usually VA is too high, equal to infinity. Then R0 is ignored. Okay. In here, you have RD. Okay. Same cases, sometimes RD is ignored. Okay. All right. So for the GM, the same GM. Okay, you need to find for the GM and also so this is how it looks like. Okay, so this is for the N channel. So N channel. So current is pointing down. Why current pointing down? You have current ID over here. Okay, so this current ID is go from drain to the source. That's why current is pointing down from drain to the source. Okay, if you have PMOS, so this current will go up, okay, from source to the drain, okay, like this. Okay, so but now we are talking about NMOS. Okay, so the AC parameter. So when we talk about AC parameter, so I always want to recall you for the BJT. So BJT for the AC parameter, you have to calculate your GM and also your R pi. Okay, if you still remember, GM equal to the IC over VT and R pi equal to Veta over GM. But in MOSFET, you also have GM. Okay, you also have GM. So, but how you calculate your GM? So, this is the ID equation. Okay, VGS minus VTH square. Okay, and GM you have to calculate your GM like this. If given, if ID is not given, then you can use GM by using this equation. Okay, VGS minus VTH. Okay, 2K. So K, this K is actually a constant value. Okay, GM also is equal to the 2K square root 2 square root KID. If ID is given, then you can use 2 square root KID. So this ID is actually represent as the IDQ and this VGS represent as the VGSQ. Okay, like when you have GM is equal to the this is for the BJT. So for the BJT, GM equal to the IC over VT. So this IC is actually represent as a ICQ. Okay, so R pi, when you calculate R pi, it is equal beta over GM. So every time it is related to the Q point. Okay, same goes to the MOSFET. Okay, so this is the VGSQ and this is the IDQ. Okay. All right. So for the output resistance, okay, so rarely ask the output resistance. So output resistance, it is actually the total internal resistance, okay, total internal resistance from drain to the source, okay. So how you can measure that is by the difference of the VDS over different of ID. All right. Okay, we have looked at the two configuration in MOSFET. Okay, so the feedback bias. Okay, feedback bias. Okay, this one feedback bias where it has R feedback over here from drain to the source. So every time you have to write your terminal. So this is your drain. This is your source. So this is the gate. Okay, the input is at the gate. Okay, the output here is at the drain. Therefore, this is common source. Okay. Okay, so now this one, the input as is for the voltage divider, input is at the gate, output is at the drain. Therefore, the left one, this is common source. Okay, same goes to your BJT. Okay, you have to specify where is your input and where is your output. Then that will be the common. Okay, sometimes the circuit is drawn the other way around or upside down. So as long as you can define, as long as you do it step by step, where is your input and where is your output, then you decide what common is the question. Okay, so this is a reminder for you for the test 2 later. So test 2 will be on 13th of June. Okay, at 9:30 a.m. So that test 2 will cover all BJT, okay, from DC analysis to AC analysis. Okay, so for the AC mid frequency, so we have common source. Okay, common source mean that source is grounded. Okay, so let's take a look on the voltage divider. So although I have some of them here, okay, but I want to actually derive it. Okay. All right, so let's take a look on the common source. Okay, so this, for example, this circuit is given. So this is voltage divider circuit. Okay, of course with capacitor. Okay, so look at so since here you already know the topic is common source, but if only you didn't, if only this didn't specify this is common source, so how you define this is common source? So this term gate is at the input, okay, okay, and output is at the drain, okay, drain, and what's left is common. What's left is source. Therefore, this is common source. Okay, still remember how to draw the AC equivalent circuit. So first thing is voltage are grounded. Okay, so this voltage is grounded. Okay, and also the all capacitor shorted. So this will be shorted and this one will be shorted. So what happened to the RS?
Short circuit.
Yes, it will be short circuit. Okay, like that. All right. So let's do on the next slide. Okay, step by step. All right. Oh, too small. Okay, so this is for the common source. Okay, so this voltage is grounded and capacitor is shorted. Okay, so this RS also shorted. Okay, so let's draw the AC equivalent circuit. Okay, AC equivalent circuit will be like this. So first thing first is to draw the hybrid pi model. Okay, you have to do some exercise on it. Okay, so the hybrid pi model is easy for MOSFET. So you have this one is gate. Okay, and then you have, since this is common source, this source is straight to the ground. Okay, so you have this source to the ground like that. Okay, and then you have plus minus VGS. Okay, plus minus VGS. So on the other side here, this is the drain. Okay, so this drain, you're gonna have the current source. Okay, in BJT you have GMV pi, but in here you have GM VGS. Okay, GM VGS. Okay, this is how you draw. So this is the hybrid pi model. Okay, so in here, I would like to ignore. So every time actually from now on, RD is ignored. Therefore, there is no RD. So this is just the hybrid pi model. Okay, so like in BJT, you draw in the R pi and then GMB pi and so on, where you put the R pi. So here we only have VGS, voltage and current source GM-VGS. So that's it. Okay, now is to draw from point to point, okay, from point to point, from gate to the ground. Okay, so let's start from the gate over here. So from gate here, you have, okay, one going to R1 to the ground. Okay, R1 to the ground. Okay, and also you from this point, okay, from this point you have R1 to the ground. From gate point also you have R2 to the ground. Therefore R1 and R2, it is actually parallel. Okay, parallel. Okay, so that's it for the gate. Okay, now let's start for the source. Okay, for the source, there is nothing here because the capacitor short and this RS short, so nothing. So source to the ground. Okay, now so this is your input. Okay, your input, your V in. Okay, so now for the drain. So let's start for the drain. Okay, for the drain, you only have RD. Okay, RD over there. So RD to the ground. Okay, and what's else? Nothing else. You only have, oops, the V out over here. Okay, V out. So if you have RL, then you have to put RL and so on. Okay, so look at the Z in and Z out. So this is your Z in and this is your Z out. So Z in is before R1 parallel with R2. Therefore, in here, this is your Z in. Okay, so and then Z naught, okay, as you can see here, Z naught is after RD, sorry, after RD. So this is your Z naught. Okay, so this is what I meant by the drawing. So in your test 2, you will be asked to draw the AC equivalent circuit with a complete labeling. So this is with the complete labeling, okay, including all the positive, minus, V pi in BJT and everything, and including the Z in and Z out. So you have to put your arrow, okay, put your arrow like this, here the Z in and the Z out, okay, in order to get full mark. So drawing this also give you 3 marks, okay, no matter what in BJT and also in MOSFET, okay. In your test 2, later you will be asked to draw with a complete labeling, so you have to draw with a complete labeling. So since you have already experienced, okay, from the common source, so if you can see here, this is closely similar to the common emitter in BJT. Okay, so when I ask you to find the Z in, okay, what can you see from here? What is your Z in? So what is your Z in over here? It is equal to what?
R1 parallel to R2.
Yes, R1 parallel with R2. Correct. That's it. Okay. And there is only VGS over there. So it is quite straightforward. Okay. How about Z naught?
RD.
So it is approximately equal to RD. Okay. It is pretty straightforward for this one. All right. Okay. And next one is AV. Okay. Let's try to find the AV. So AV is equal to the V out over V in. So for V out, okay, same like in BJT, what will be the V out? Okay, V out is I times R. Okay, so this V out. Okay, so this V out. Okay, so this V out, this positive minus V out. So this V out is the voltage across RD. Okay, voltage across RD. So we know that you have to put RD over here. So what will be the current here? So what will be the current over here? What will be the current over here? It is
minus
yes.
GMVGS.
Yes, minus GM VGS, okay, times RD. Why minus? Because this current source is in opposite direction, okay? It is going down, but we want current going down here. Therefore, you have to take the negative direction of this GM VGS. That's why you put negative GM VGS times RD. Okay, in this case, only you have RD. But if you have RL, then you have to parallel with RL. Okay, what will be your V in? Okay, what will be your V in?
VGS.
Yes, it is equal to the VGS. Why? Because V in over here is parallel with this VGS. Okay, so you can straight away take V in is equal to the VGS. Okay, now you can cancel out this VGS. Therefore, it is equal to the negative GM RD. Okay, so it is quite straightforward. Okay, for the common source. Okay, for the common source MOSFET. Okay, all right. So okay, so this is the same thing over here. Okay, same thing. And this is also the same thing. Okay, if it include RD, so RD is very, very large. Okay, usually we can ignore this RD and Z out is approximately equal to the capital RD. Okay, we can ignore the small RD. All right, so let's take a look on the example. So let's do it together. Okay, for this one, yeah, so this is last time, I mean past year, like past year, I think. Okay, all right, so basically for this one, you have to do from the scratch. Okay, so you have, if you look at the question, okay, find VGSQ and IDQ by graphical method. Okay, so this one you need to, if you still remember, you have to draw the ID. So ID is equal to K VGS minus VT square. Okay, so you have to do this. So VTH is given 2 volt. Okay, I don't want you to waste time. Okay, so let's say you have done this. Okay, so I will just give you the VGSQ and IDSQ. Okay, so if you want, if you have time, okay, later you can do it yourself. Okay, to find the VGSQ and IDQ. So how to find the VGSQ and IDQ by graphical method? You can refer to the previous slide. Okay, so where you have to plot the IV characteristic, if you still remember. So this is what we have done during the before semester break. Okay, and then you have to find this load line. Okay, so this is the load line. So how to find this load line is from the input loop. Okay, from input loop. For BJT, you do it for output loop, but for this one is from the input loop KVL. Okay, and then this is your Q point. Okay, you can do it later, but I have done it. So basically IDQ is equal to the I will write it here. So IDQ is equal to the 2.8 milliampere and VGSQ is equal to 4.3 volt, right? So if you do the graphical method, okay, this one you will get this. Okay, now I want to focus on the draw midband and so on, right? So let me copy first this one. All right, so this one, if you look at the question, number 2, draw the mid-band AC equivalent circuit. Number 3, find the impedances Z in and Z out. And number 4, find mid-band voltage gain, AV, V out over VN, V in dB. All right, so let's do it. Okay, so this is example 1. For the common source. All right, so first thing first. So first thing first is all the voltage is grounded. Okay, all DC voltage grounded. Okay, so this one will be grounded. Okay, on that one. Okay, if let's say, okay, so this is maybe hint. Okay, if let's say you have a voltage at the bottom over here, so means that you have positive 18 and then you have negative 18 over here, so this voltage also will be grounded. Okay, now it is to the ground, therefore it is ground. But if you have the back-to-back source, voltage source up and down, so both voltage will be grounded. Okay, so next is all capacitor. Okay, is short circuit. Okay, so this capacitor will be short circuit. So this capacitor will be short circuit. This capacitor will be short circuit. Okay, so since CS is short circuit, what happened to the RS over here? Will be?
Short circuit.
Yep, it will be short circuit. Okay, so if you keliru, okay, if you feel like you're confused, so you have to write down the terminal. So this is the gate. This is the drain and this is the source. Okay, so since the input now, input means, what I mean by input is the voltage at input. So this is your input. Okay, so input here is connected to the gate. Okay, and output means where your V out is. So this is your output. So now output is at the drain. Therefore, what's left is source. Now this is common source. Okay. Okay, this is what I meant. On BJT also something like that. Okay. Okay, now let's draw the AC equivalent circuit. Okay, first thing first is to draw your GM VGS, your hybrid pi model. Okay, hybrid pi model. So you have here gate. Okay, now you know that your source is straight to the ground. Okay, because there is no resistor. Okay, you can draw your source like this. So this is your source to the ground. Not to forget, you have your voltage over here, VGS. So this is the hybrid pi model for MOSFET. Okay, and also you have the current source over here is GM VGS. Okay, GM VGS. So this is your drain terminal. Okay, drain terminal. So drain terminal, okay, let's start from the source straight to the ground. Okay, so there is nothing, no resistor at the source. So let's look at the gate. Okay, at the gate over here, you have uh, R1. Okay, you have R1 and you have R2. Okay, R1 to the ground, R2 also to the ground. Therefore, you have R1 parallel with R2. Okay, and then what's else? You have this capacitor C1 is short circuit, and then you have V in over there. Okay, so you have your V in. So this is your V in. Okay. Okay, this is your V in plus minus V in. Okay, and then at the gate is done. Okay, so let's do it at the drain. Okay, so what it is? Okay, okay, at the drain. So at drain, what do you have? You have here RD to the ground. Okay, you have RD to the ground. Okay, but not finished yet. At the drain also, you have capacitor C2 short circuit and you have RL. Okay, RL. So the V out is across RL. Okay, so this is the V out. All right. Okay, so do not forget to put your Z in and Z out. There are supposed to be in the question, there's supposed to be this is your Z in, okay, and this is supposed to be your Z out. Okay, so this is your Z in. Okay, usually they will put arrow. Okay, this is Z out. Okay, so that's it. Okay, so this is AC equivalent circuit with a complete labeling. So this will give you 3 marks. Okay, quite a lot of mark. Okay, in BJT as well, you will be asked to draw the AC equivalent circuit. So please draw it properly with complete labeling. All right, so next is to find all the values. Okay, all the values. Okay, for the Z in, Z out, I will do it in this slide. For the AV, I will do in the next slide. Okay, so first this one done. Okay, the input and output impedance. Okay, input and output impedance Z in and Z out is equal to the R1 parallel with R2. So this one R1 is equal to R1 is equal to the 4.7 mega. Parallel with R2 is equal to the 2.2 mega. So this one will give you about 1.5 mega ohm. Okay, for the Z out, okay, Z out is equal to what? Do you have to parallel with RL? Z out is equal to?
RD.
Yes, it is equal to the RD, which is equal to the 2.2 K ohm. All right, so that is for the Z out and Z in. So let's take a look on the AV. Okay, AV. Right. We do it on this next slide. Okay, so for the AV, okay, AV is equal to the V out over V in. Okay, so AV, okay, AV is equal to the V out over V in. Okay, so V out is total, is the voltage across two resistors. As you can see, your V out is over here. Okay, over here. So this V out is actually voltage across RD parallel with RL. Okay, so you have here the total resistor is RD parallel with RL. Okay, what about your current? So current in opposite direction. So you're going to take the current source over there, GM VGS with negative. Okay, with negative. Okay, and then V in, okay, V in is equal to the VGS. Okay, as you can see, this V in, okay, this V in is parallel with this VGS in the same node. Therefore, V in is equal to the plus VGS. So V in equal to the VGS. You cancel out this, you could get that negative GM RD parallel with RL. All right. Okay, so now where do you have the RD and RL? Okay, you need to find your GM. So if you look at this one, okay, in order to find GM, it's either you can use this one or this one. Okay, I already have the value just now for the VGSQ. And also VTH is given, but you can also use the formula down there, 2 square root K IDQ, you will get the same answer. Okay, the same answer. With if only the threshold voltage is given and IDQ given. Okay, so we're gonna do both. Okay, to look at so that you'll be familiar. Okay, so GM is equal to the first one is 2K Okay, VGSQ minus VTH. Okay, so look at the question. So VTH is given 2 volt. Okay, and K parameter also given 0.5 milli. Okay, therefore this one you will get 0.5 milli. Okay, times VGSQ. Okay, from the load line you should get VGSQ 4.3. Okay, 4.3. So 4.3 minus your threshold voltage just now given 2 volt. Okay, here you will get 2.3 millisiemens. So that is for the first one. Okay. All right, so for the second one, you can or you can calculate GM by using 2 square root K IDQ over here. Okay, so K is given 0.5 milli, IDQ also given 2.8 milli. This is not given. You can do it later using graphical method. You should get the same answer like this. Okay, so IDQ 2.8 milli. Right, so 2 times here 0.5 milli. Okay, and this is 2.8 milli. Okay, you should get the answer here closely similar 2.3 millisiemens. Okay, both are the same answer. Okay, you can plug in the calculator now to prove the both answer are the same. Okay, so back to the question. So this one negative GM is negative 2.3 milli. So RD is actually 2.2 K. Parallel with RL is 1 K. Is it? Yes, RD 2.2 K, RL 1 K. All right. So this one is equal to the negative 1.63. Okay, but in the question they ask you in dB. Okay, how you convert in dB? How to convert in dB? So AV in dB is equal to, how to convert in dB? 20.
20
Yes.
log.
Yes, 20 log AV. So you should get this one about, I didn't calculate. Can someone calculate for me?
Ma'am, we take the absolute value of AB, right?
Yes.
Okay, so 4.24.
Okay, 4.24 dB. All right, that's it. Okay, so this one is done. Okay, for the AC equivalent circuit common source. Okay, for common source, this is quite straightforward. So basically, for me, MOSFET is much simpler than BJT. Okay, but MOSFET will only be asked in the final exam. Okay, BJT will cover in the test 2 whole. Okay. All right, okay. So I think so this is for the common source. Okay. Next one is the common drain. Okay. So this is pretty similar to the voltage divider. Okay, but then as you can see from here, how we define whether this is common drain. So now it is already being shown here. It is common drain. Let's say it is not written over here. Okay, how you define whether this is common drain. So look at the okay, write down everything. So this is gate. Okay, so this is the drain. This is the source. All right. Okay, so if you look at the input, so the input means this voltage source. Okay, this is the voltage source at the input. Okay, now this voltage source is connected to the gate. Okay, to the gate. Therefore, this is the input. Okay, now the output over here. Okay, output means this RL. Okay, this is your output. Okay, this is your output. Now output is at source. Okay, what's left over here is drain. So that's why this is common drain. Okay, that's how you define it. Okay, whether it is common source or common drain. So for this case, the input is at the gate, the output is at the source, and what's left is drain. Therefore, this is common drain. Okay, yeah. So this one to be derived in class. Okay, which is today. Okay. All right. So give me some time to copy. Okay, let's take a break, 5 minutes, okay, before I copy this one.
Doctor, can you give us attendance?
Yes. What?
Can you give us the attendance, please?
Oh, yeah. I have told in the earlier class, okay, from now on, there will be no scanning attendance because I will take your attendance from my Webex log report, okay, where I can see who's come in and who's not come in and from what time to what time you join the class, okay. So I'm not wasting time to giving you attendance after this, okay. I will just take the log report from my Webex.
Okay, doctor, thank you.
Okay. All right. Okay, so let's start. So this is for the common drain. Okay, like I said, common drain is it is similar in BJT common collector. Okay, if you still remember for the common collector. All right, for the common collector, okay, for the common collector, let me show you for the common collector if you forgot. Okay. Okay, so this is how it looks like for the common collector. All right, so for the common collector, you have base, emitter, and so on. So this is common collector where collector is grounded. Okay, so collector is grounded. You have voltage source GMV pack, and you have output at the emitter over here and input over here. So this is how it looks like for the common collector. Okay, for the Z out, okay, if you still remember, you cannot take straight away equal to RE where you have to find the Z test. Okay, Z test. Okay, in order to find Z test, you have to inject the V test. Okay, if you still remember, you have to inject the V test. Okay, so in order to inject V test, okay, you detach RE and then you inject V test and you find Z test over here. Okay, so same thing in the common drain, we will do the same thing over here in common drain. Okay, after you get Z test, okay, Z test is equal to the V test over I test. Okay, then you have the equation for Z test, this one. Then only you parallel with RE. That will be your Z out. Okay, same goes to the common drain over here. Okay, let me go back to the slide over here. So same goes to here, okay, where you have to apply Z test. Okay, now let us draw, okay, analyze the AC equivalent circuit, okay, for this one. All right. Okay, for this one, you have here, this is your gate. Okay, this is your drain, this is your source. Okay, so this is the common drain. Okay, common drain. All right, so first thing is DC voltage grounded. Okay, so this is ground. All right, only one DC voltage, and all capacitor is short circuit. Okay, so this C1 will be short circuit and this C2 will be short circuit, and what else? Nothing, only two capacitor. Okay, C1 and C2 are short circuit. Okay, so now let's draw the AC equivalent circuit. Okay. Okay, for the AC equivalent circuit. All right, so first thing is to draw your GMVGS. This is your gate. Okay, this is your drain. Okay, where you have here your current source, GMVGS. Okay, and this is your source. Okay, and you don't forget you have your VGS over here. Okay, so let's start from the source. Okay, from the source. Okay, as you can see from source over here. So let's start from the source over here. Okay, this is source. So let's start here from the source. Okay, from the source over here, you have what? You have RS. Okay, as you can see, you have RS to the ground. This is same like common collector. So from the source here, you have RS to the ground. Okay, and also from the source as well, over here you have RL to the ground. Okay, why? Because output is at the source, so you have RL over here. Okay, to the ground. So this is your RL. Okay, and your V out is across RL, like that. Okay, so now let's take a look on the drain. Okay, so drain. So drain, there's nothing there, no resistor and everything there at the drain. Therefore, the drain is, oops, wait. Okay, therefore drain is grounded, like that. Okay, and next is at the gate. Okay, at the gate, of course, this is voltage divider. Therefore, at the gate you have from here to the R1 and from here to the R2. Okay, therefore straight to the ground. Therefore, you have R1 and R2 is grounded. Okay, R1 parallel with R2. Okay, what else do you have? Okay, so you also have here, so I want to draw like this, down. Okay, so at the gate also you have capacitor C1 short circuit and R signal to the VS. So you have here RS and V signal. So this is your VS, so this is your R signal. Okay, why it is written as a R signal instead of RS? Okay, because we don't want you to get confused, okay, with RS. So at the front there, R signal, at the source terminal there is RS. Okay, so this is how you draw the AC equivalent circuit for common drain. Okay, it is pretty similar to the common collector. All right. Okay, so wait a second. Okay, now let's put the Z in. Okay, if you can see here, so this is your Z in just before R1 and R2. So this is your drawing. Okay, so this is your Z in. Okay, and Z out over here, as you can see over here. So Z out is V4 RL. So this is your Z out. Okay, Z out. Okay, so if you want to draw a line also here doesn't matter. Okay, so this is how it looks for the AC equivalent circuit common drain. Okay, now let's do the analysis. Okay, to find the Z in, Z out, as well as the AV. Okay, AV. All right, so for the Z in, it is quite straightforward. Okay, Z in, because there is open circuit over here. Okay, there is like a break over here. Therefore, Z in is just R1 parallel with R2. Okay, Z in is just R1 parallel with R2. But Z out now, if you can see from here, so Z out, it is you cannot take this resistor. Okay, you have to take at the input as well. Okay, because there is a voltage current source over here. So you have to consider the imaginary voltage Vtest. Okay, so we're gonna do the same thing like I've shown you in the common collector just now. Okay, where we detach this RS and we put Vtest over here to find the Z test. Okay, then only you will get your Z out, which is Z test parallel with RS. Okay. Right, I need to copy something. And you wait. All right. Okay, so just want to recall. Okay, so this is equivalent circuit for common collector. So you can see it is similar, right, for the common drain just now. So the collector now is grounded. Okay, you have to find the Z out over here. okay, with the V test and I test. Okay, if you can see from here, so we detach RE and we inject V test, okay, minus plus V test because current going down, therefore minus plus, and then we find V test. Okay, how to find Z test? It is actually equal to V test over I test. V test is the voltage across this loop, total voltage across this loop, over I test. Okay, like this. Okay, like this. So for the V test over here, voltage across this loop, so you have to consider this one, RB, IBRB, and also IBR pi. Okay, then you get the total voltage V test. Okay, however, for the I test is equal to the IE. Okay, IE, you know that IE is equal to the beta plus 1 IB. Okay, that's why you get the simplification. Okay, finally, V test over I test is equal to the total voltage V test over I test. So you cancel out IB, so RB plus R pi over beta plus 1. So this is how you get the V test. Okay, why I show here? Because I want you to recall. Okay, we have done this, okay, for the V test for common collector. So we're going to do this again for common drain. All right. So I have copied what I've drawn just now. Not good, but okay lah. Tadi tak ada. Okay. Alright, so let's derive. Okay, for this one, we already have the Z in R1 parallel with R2. Okay, now we want Z out. Oh, is there any question? Doctor, I joined with this. Okay, doesn't matter. Join with phone doesn't matter. Okay, all right. Okay, so for this one, VS, IS. All right. Okay, so let's derive now. I want to derive for the Z test. Okay, Z test. Okay, so Z test, like I said just now, we detach RS and we inject. Okay, so this one. Okay, Z out. Okay, you need to find Z test. So we inject, we detach RS and when we inject. Okay, so that I want to draw, okay, to find, okay, Z test. Okay, inject V test. Okay, okay, detach RS. Okay, so now let's draw together. So you have heat drawing. Okay, so you have here, what is this? Okay, GM VGS. Okay, we detach RE. Okay, we inject over here is V test. Okay, and then this is your I test. Okay, so this one, it is actually you detach the RE. So basically, this is your RS and this is your Z test. Okay, your objective now to find your Z test. Okay, so you have over here, sorry, wrong drawing. So it's like this. This is ground. Okay, since this is your drain, this is your gate, this is your source, therefore you have over here is VGS. Okay, like that. So that is your VGS. So this is how the drawings looks like. Okay. All right, so to find the V test, okay, if you can see here, there is no resistor. In the common collector, you have resistor everything. Okay, over there you have resistor. Okay, now you only have VGS. Okay, if you look at this one, okay, if you look at this one, so basically, okay, from the source to ground, you can actually see these two resistor. Okay. So basically, if you draw upside down, you will get that your VGS, okay? So since for this one, you inject V test, so V source will be grounded. Okay, V source grounded. So only voltage available here is V test. Okay, so this one is grounded. So let me highlight over here. So this one is grounded. Therefore, V test is actually equal to, in this case, V test is connected to the gate and source. Therefore, V test is equal to the negative VGS. Okay, V test equal to the negative VGS. Okay, if you can see from here. Okay, sorry. Okay, so this is your V test. Okay, so at this node, okay, only you have, if you apply KVL over here, so that is, okay, let me draw you over here again. So this VS is shorted, so you have over here is what, R1 parallel with R2, right? R1 parallel with R2 and also parallel with R signal. Okay, oh, R1 parallel with R2, parallel with R signal. Okay, so why? Because this IG is always approximately equal to 0. Okay, when IG approximately equal to 0, this one will be short circuit. So when this one short circuit, okay, therefore V test is, as you can see, so V test over here, I think I need to draw a different color. Okay, draw again. Okay, so this one, sorry. Oh, okay, so IG is 0. Okay, this one will be short circuit. Okay, and this node, okay, this node of V test is connected to the plus here. Okay, if you apply KVL over here, you will get V test is equal to negative VGS. Okay, that's why we get there V test is approximately equal to the negative VGS, because IG is 0 and R1 parallel R2 parallel R signal is also short circuit, and V test is connected to the VGS, and you apply KVL, you will get a V test negative VGS. All right, next one. So I test. What is I test equals to? Someone? I test?
GMVGS.
Yes. Yes, correct. Because it is in the same direction, therefore GM VGS. Okay, so Z test, okay, is equal to the V test over I test. Okay, and equal to the negative VGS over I test is GM VGS. Therefore, you will get negative or positive. Sorry. If you apply KVL over here, so you will get
V test equal to
is it
VGS, right?
yes,
negative one.
positive VGS. No negative, yes, no negative. Sorry, yeah. If you apply, let me do highlight. Okay, if you apply KVL over here, okay, you should get it is positive VGS. Okay, positive VGS. So therefore, this one, the exact test is equal to 1 over GM. Okay, 1 over ZM. Okay, so go back to your Z out. Long story over here. So Z out will be equal to the RS parallel with Z test, which is equal to RS parallel with 1 over GM. Okay, so this is your RS. Okay, let's see. You don't want to for the Z test, okay, for the Z test, you don't want to derive it. Okay, in the end, your IG here is 0. Okay, in the end, your IG here is 0. So this will be short circuit. So this is applicable for the MOSFET only. Okay, because IG 0 and this one short circuit. Okay, finally, you will get 1 over GM. Okay, if you don't want to draw and derive, you can straight away write that Z test is equal to 1 over GM, and you can calculate straight away RS parallel with 1 over GM. Okay. If only the question asks you to derive for Z test, then you have to derive. Okay. Okay, but the rest, for the AV and everything, you need to derive. Okay, not a very complicated derivation. Okay, for the AV and everything, you just, what I meant by derive is V out over V in. Okay, what is your V out? So you have to write here. What is your V in? You have to write it. You don't simply put like this. Okay, equal to negative GM RD by VRL. That means you memorize it. Okay, so you have to derive. So in the test later, BJT, they also ask you to derive AV. So AV, when derive, means what is V out, what is V in, you write it, and finally you get this. Okay, this is for MOSFET lah. And for BJT, you have to derive. Okay, all right. So let's take a look what else. Okay, now we have done on the Z in and also for the Z out and Z test. Now let's take a look on the V out over V in. Okay, so I want to do on the different slide. Okay, it will be messy if I combine it. Okay, all right. All right. Okay, so AV, so let's derive together. So AV, okay, is equal to the V out over V in. Okay, so now what is the V out? Okay, so let's take a look there. So your V out over there is equal to, I want to write it here. Okay, so V out over there is equal to what? Okay, V out is equal to total current times total resistor. As you can see here, V out is parallel with RS and RL. So meaning that V out is across these two resistors. Okay, so you have to parallel RS and RL. Now, what about the current? So what about the current over here? Do you have to put negative, or you can straight away take GMVGS? Okay, current is going down. Yes, GMVGS. So current is going down to the plus. Okay, current is going down to this plus V out. Therefore, it is plus. Therefore, it is plus GM VGS. Okay, so sorry, I have to go back here. Okay, why we take this negative? Okay, because now current is not going to the plus V out. It is in the opposite direction. Instead of going to the right, it is going to the left. Okay, that's why we put negative over here. Okay, different case with this one. Okay, it is going into the plus V out, therefore it is plus. You don't have to put negative. All right. So now what is for the V in? Okay, V in is across here. So this is your V in. Okay, what you can see from here, the V in, okay, remember your objective is to simplify the equation. So V in is voltage across R1 and R2, right? Okay, but then you want to simplify it. So all these are in parallel. Therefore, V in is total voltage from the gate to the source, to the ground. Okay, V in from the gate to the ground. Okay, what you can see from the gate to the ground, first thing you see this voltage, VGS. Okay, you write it first, VGS, but not finished yet because you have another voltage, okay, from source to the ground. So what voltage is this? So what voltage? So V in is VGS and also voltage at the source. So what voltage at the source it is? So it is the same voltage as
V test.
not Vitas, not Vitas.
V out.
It is yes,
VS.
it is VS, it is VS, and it is V out as well. Okay, As you can see, the V in is total voltage from gate to the ground. Okay, what you can see from the gate to the ground is first VGS, just up to the source, not yet to the ground. But from the source to the ground, you have VS. So VS is actually voltage across these two resistors when you have two parallel, and it is equal also to the V out. Okay, same thing. Okay, so you can take all the portion over here, which is equal to GMVGS, RS parallel with RL. Okay, all right. Anyone? Oh, sorry, VGS over here. So, all right, everyone clear? Okay, so
Yes.
yes, okay. So you have to cancel out this VGS. So this equation will be simplified as GM RS parallel with RL. What is the simplification? 1 plus GM RS parallel with RL. Okay, so this is how we get the AV. Okay, we get the AV. All right. Okay. All right. Any question?
Yes, doctor.
Any question? Hello? No question. Clear?
Yes, clear.
All right, clear. So, yeah. Got one question. Is RL parallel, is RS parallel RL or Z out parallel RL? Okay, remember that every time you find V out, okay, there is nothing to do with the Z out. Okay, in this case, V out is voltage across these two resistor. Okay, these two resistor. You just take the resistor is RS parallel with RL, not Z out. Okay, Z out, okay, only you do it for the Z out where you inject V-test and everything. Okay, when you inject V-test, you didn't consider this source voltage. Okay, VS you didn't consider. Okay, because you inject imaginary voltage over here and this V source is ground. But when you find V out, we have to put back this VS. Okay, we don't have imaginary voltage. Therefore, you have to take the voltage across V out is RL parallel with RS. Okay, not Z out. Is that clear, Sangkai? All right. Okay. All right. Okay. I think that's it. Okay. The derivation for the Z in, Z out, and AV. Okay. I think for the MOSFET, why Benzen asks why I out is GMVGS? Why out I out is GMVGS? Did I say I out GMVGS? Oh, okay. So why I out GMVGS? Okay. Oh, I think his question, I think we out there. So Vincent asked why I out GMVGS over there. Here, okay. Same goes to the common collector. Okay, so you take the current from the GMV pi. Okay, from here, Y I out is equal to the V out because if you parallel these two resistors, it will become one resistor. So the current at this V out one resistor, I mean RS parallel RS is IS, right? So IS, right? Okay, so here is ID. So here is IS. Okay, we know that approximately ID approximately equal to IS. That's why we take GM VGS here. Okay, it is the same thing. Okay, equal to GM VGS. Okay, because the current is approximately equal to ID, approximately equal to IS. Same goes to the common collector. So current is IC approximately equal to IE. That's why we take GM V pi only. Same goes to here. All right, Vincent. Okay, great. Okay. Okay, so we have derived for the common drain. Okay, now let's try this example. Okay, so I think this is the final example. Next class we will continue on the common gate. Okay. I think I'm quite slow today, but that's okay. I go through very slow. Okay. Why? I need you to. Yeah. Oh, okay. So how about V in? Why parallel RS and RL we add together like it's in series? In series? So Benzen asks, oh, okay. How about V in? Why parallel RS and RL? We add together like it's in series. Again, let me read the question. Okay, how about V in? Okay, so how about V in? So this V in, okay. Why parallel? How about that V in? Why parallel RS and RL we add together like in series? Okay. If I understand your question, so you mean that why this V in is in Y parallel RS? Okay, so why is this total this one you mean? Okay, this one? Yeah. Because, okay, Benzen, because this is okay, remember, so every time you find a V, okay, you need to simplify your equation. Okay, not only Benzen, all the students, you need to simplify your equation. What can you simplify from here? Okay, as you can see, this V in, okay, from gate to the ground. Okay, this is your gate, okay, to the ground. Okay, what can you take in order to simplify your equation? So take all the parallel thing over here. Okay, so from the gate to the ground, what can you do? You cannot take R1 and parallel R2 because you don't know the current over here. But you can make use of what can you see from gate to the ground over here because it's in parallel. The same wire over here at the gate, the same wire over here at the ground. Okay, so I make use from here. So what can you see? It is the total voltage from gate to the ground. Okay, from gate to the ground. Okay, so what can you see parallel in here? So from gate to the ground, what can you see over here? You can see VGS. Okay, that is 1. Okay, and then you can take or you can plus also. Okay, this one it doesn't look like it is in series. Okay, because it break into 2 resistor. Okay, imagine that you already parallel these 2 resistor. Okay, it become 1 resistor. Then you can see it is in series. Okay, so you have this one VGS. And then you have another from this gate to the ground, you have gate to the source 1 VGS over here, and also in series as well at this node from source to the ground is these 2 resistor which already being parallel into 1 RS parallel with RL. What is the voltage across here? It is the voltage, these 2 parallel resistor, the voltage across there is V out. It is the same thing what you have done on the top over here. Therefore, it is V out. Or if you confused, you didn't see V out, it is VS. VS. KVS. So VS is voltage. You need to parallel these 2 resistors because 2 resistors in parallel. Okay. Because VS is RS parallel with RL. What is the current across this source? The current across this source is IS. And you know that IS is approximately equal to ID. So ID, current source over here, equal to GM VGS. That's why you multiply GM VGS. It looks like in series, Benzen, if you imagine these 2 parallel and become 1 resistor.
Yeah. All right, thank you, doctor. I get it.
Welcome. Okay.
Thank you.
All right. Okay. So not finished. Okay. Let's take a look on the example to be much more clearer for all of you. Okay. So in this example, same. Okay. Not same. Same. How you want to calculate? Oh, because you don't have. Okay. Doesn't matter. I hope I have the example. Yeah. Okay, so in this example, it is actually you have to find what is the VGSQ. Okay, so read. Can you read the question first? Okay, so determine R1, R2. Oh, it is more on the DC analysis. Okay. Okay, VDSQ is given 3 volt and then calculate the AV, draw AC equivalent circuit. Okay, so for this one, okay, let me see whether I have the. So what are given over here? Oh, ZAC in is given 300 300 kilo ohm. So this is a design question. Oh, yes. Okay. So you definitely going to see this kind of question in your test 2 BJT. Okay. Given backward where you have to find the resistor value. Okay. I think I have put some question in the tutorial. Okay. So you read the question first before, because I think this is not much on the information over here. Wait. Mm-hmm. So IDQ. Got cell not given. Mm. Oh, so this question. Oh, okay. So given IDQ, okay, 1.7 milli and VDSQ 3 volt, okay, draw the AC equivalent circuit. Okay, so you have to draw the AC equivalent circuit without all the information there. Okay, wait. So R1, R2. I think some information missing over here. So this will be number 2. Okay, I think some information missing. Okay, doesn't matter. Okay, let's do the draw AC equivalent circuit. Okay, but we will do number 2 as well. Okay, let's draw the AC equivalent circuit. Okay. Okay. All right, okay. So for this one, if we want to draw the AC equivalent circuit, okay, we don't know yet whether this is what common. So for imagine that you don't know yet. So this is gate, drain, and source. Okay, the input here. So this is the input. Okay, and this is the output. Okay, input at the gate, output at the source, and this is common drain. Okay, so let's draw first. Okay, on the AC equivalent circuit. Okay, so if we want to draw the AC equivalent circuit, it is like pretty similar to what you have done in the previous slide. So this is common drain. Okay, if you draw it again, okay, you have to draw many times. So it will be a good practice for you. So you have what you have? Okay, you have here gate. And then you have drain, and then you have the GMVGS. Okay, this is your source. Okay, you have here VGS. Okay, and then from source over here. Okay, let's start from the source. So from source you have RS. Okay, and then this one short. Okay, this one ground. Okay, I didn't write, but you know it. Okay, so from the source you have RS, and then you have RL. This is your RL. Okay, drain now straight to the ground. So green is to the ground. Okay, and this is your V out. Okay. Okay, this is your ground. Okay, at the gate here, at the gate you have R1 parallel with R2. Okay, because R1 to the ground, R2 also to the ground. Therefore, you have R1 parallel with R2. Okay, so R1 parallel with R2 is equal to this one. You have short to the V in. Okay, to the V in. So you have short circuit to the V in. All right. So this one, put your Z in. So this is your Z in, and this is your Z out. Okay. All right. So this is how it looks like for the AC equivalent circuit, where you have everything there. Okay. For the Z in, Z out, V in. Okay, V out. Okay. So this is your V in plus minus V in. All right. Okay, so for this one, determine RS, R1, R2, so that IDQ is 1.7, VDSQ. I think this is some missing over here. Let me think about it. So is Sag-in given? Sag-in is 300 Kelvin, is 300 kilo. Is V out given? No. You can find GM because ID is given. So RS, find RS. I think from the DC analysis. VDSQ given, you have VDS, RS. VD, VDS. Okay. Okay, so I think I know. All right, so we have to do it. So this is quite, I think they mix with the AC and DC. Okay, so this one for the AC equivalent circuit. So first they ask for the AC equivalent circuit. Next is determine RS and R1. So this one is DC. Okay, DC. Okay, DC analysis. Okay, for the DC analysis, you have to draw the input loop and output loop. Okay, if you still remember. All right, so I think we can do it. Okay, right. So this one you have over here. All right. Okay. So, all right, right, right. Okay, okay, okay. Okay. So, I will put this question as one of the tutorial question. We will discuss on the tutorial. Okay. But this one is for the DC. Of course, your tutorial will be part 1 DC, part 2 AC. Okay. I don't want to mix with DC and AC. Okay. This one can be solved using AC as using DC analysis. Okay, what you can do is you have to draw. Okay, if you still remember. Okay, you have to draw. So this is at the input. Okay, this is at the output. You have drain. Okay, and then you have here is okay source. So this is your source. Okay, you have the RS, and then at the drain also, because for DC analysis, okay, capacitor is open circuit. So this is open. Okay, this is open, no RL. At the drain only you have here to the VDD. Okay, to the VDD, and then you have like this. Okay, VDD. All right. So in the question, they said given VDSQ. Okay, VDSQ is given. So this is what they meant by this VDSQ. Okay, IDQ also given. Okay, IDQ 1.7 milli. So IDQ here given. Okay, 1.7 milliampere, and VDSQ 3 volt. Okay, 3 volt. Okay, so you can apply KVL over here. Okay, VDD also, you know, 5 volt. Okay, you can find RS. Okay, so this is DC analysis. So this question is mixed between AC and DC, but I will put this DC analysis in the tutorial question. Okay, but you can solve this using DC analysis in order to find RS. Okay. Yes, can be solved, and yeah, doesn't matter. We do it in the tutorial. All right, since we have time, I think I want to, since we didn't finish the question that one, okay, for the DC and SE, okay, but then, but then I didn't calculate, I don't know. Okay, but yeah, we do it for the DC in the tutorial, but then how you find, okay, so this is the drawing the AC equivalent circuit. Find Z in is pretty similar to what I have derived over here. Okay, very similar. Find Z out also, you can straight away RS parallel with 1 over GM, and then AV is like this, okay. Okay, I will give more example in the tutorial, okay, for good exercise. All right, so now for the common gate, okay, so for common gate, it is similar to the white common. Still remember? White common in BJT?
Common base.
Common base, okay, common base, okay. So we write again over here. So this is your gate. So this is your input, okay, at the drain. No, at the source. Okay, and also you have output. This is your output, okay, output at the drain. Okay, now this is common gate, okay, common gate. Okay, this is good question. Okay, so as you can see, for the common gate, okay, there is a voltage at this going down over here. Okay, but doesn't matter, we can derive this. Okay, we can derive this. Okay, so let me copy it up. All right, so in order to draw the AC equivalent circuit, okay, AC equivalent circuit, okay, what you should do first thing first is DC, okay, grounded. Okay, so this DC, so you have this DC grounded, okay, and all capacitor short circuit, okay, capacitor short circuit. This one short circuit, and this one also short circuit. Okay, same like common base. Okay, how you draw the common base? Okay, yeah, that's why I said today's class quite slow, because I want to show you what you have done for BJT. So this is BJT. So if you still remember, we have derived for the common base. So for the common base, this is how it looks like. Okay. Okay, so for the common base, so you have base to the ground. Okay, if you draw the AC equivalent circuit, you're gonna have GMV pi in horizontal like this, and then you have R pi. So this is your hybrid pi model. Okay, hybrid pi model. So this is your hybrid pi model in the yellow box. Okay, you have R pi, GMV pi, and base to the ground. Okay, I hope you still remember this. Okay, now for the common gate. Okay, let's draw. So you have okay, in this case, so this is okay, you have GMVGS in horizontal. Okay, so this is your GMVGS, and this is your source, this is your drain. Okay, so now the current is from drain to the source. So this is your drain, this is your source, this is your gate. Okay, remember for N channel current ID is going from drain to the source. Okay, if we draw the symbol, okay, so this is the symbol. Okay, so this is the gate. So this is the drain, gate, and source. So this is N channel. Okay, N channel. So current going from the drain to the source. Okay, that's why current going drain to the source to the left, and your GM VGS also to the left, like this. Okay, and your hybrid pi model is not complete if you didn't write your VGS plus minus VGS. Okay, now your gate, you have no resistor over here, so it is straight to the ground. Okay, therefore your gate here is to the ground, like that. Okay, and not to forget, you have to put your VGS. Say this is your VGS. Okay, remember that since this is N channel, therefore plus at gate, negative at source. Okay, same like what we have done in the previous slide. Okay, so VGS always that the always for N channel. Okay, plus at gate, negative at source. Okay, same goes to here. Okay, so we have done the hybrid pi model. At least you have drawn the hybrid pi model for the VGS and also GM VGS. Okay, now is to put all the component. Okay, at source. Okay, at source over here you have RS to the ground. Okay, RS to the ground, and this C1 is short circuit to the R signal and to the VS. Okay, V signal. Right. So you have V in. Okay, you have V in and Z in. Okay, you have V in over here and Z in over here. Okay. Now at the drain, okay, at the drain, since this has become grounded, okay, at the drain you have RD. Okay, and also you have short circuit C2 to the RL. Okay, RL. All right. So this is your V out, and do not forget your Z out over here. So this is your Z out. Okay, so this is how you draw a complete, with a complete labeling, the AC equivalent circuit for the common gate. Okay, pretty similar to the common base. Okay, I hope you all clear. All right. Okay, so for the Z in, okay, Z in is quite straightforward. So Z in is approximately equal to RS. And then for the Z out, okay, you only see RD, therefore it is equal to the RD. Okay, so for the common base, same like for the common gate, same like common base, quite straightforward. Okay, if let's say you have RG over here, okay, oh my god, okay, if let's say you have RG over here, okay, if let's say you have RG over here, you don't have to put the RG in your circuit. You don't have to put your RG at your gate. Why? Can someone give me the reason why? If you have RG, if this circuit is drawn with RG, in AC equivalent circuit, you don't have to draw the RG. Why? Yes, Bayesian said because IG equal to 0. Okay, IG always equal to 0, and it is like short circuit. If there is a RG, but RG is 0, it is short circuit. So you don't have to draw the RG in your AC equivalent circuit. Okay. All right. So now we've done for the Z in and Z out. Okay. Next is to see the AC equivalence. The AV. Okay. This is quite straightforward. Okay. Wait, I need to copy. All right, so let's derive for the AC for the AV. So AV is V out over V in. So V out, can someone give me what is V out, please? So the The hint is V out is across RD and RL. So I give you the hint. So RD parallel with RL. Okay, what will be the current over there? Someone?
Negative GM VGS.
Yes, correct.
Ah,
Negative. Yes, negative GM VGS. So that will be the V out. Okay, what about the V in? Someone? V in? What can you see from there in parallel with V in? So this is your
negative VGS.
Yes, so this is your V in. So you have V in from source to the ground. What you can see from source to the ground is negative VGS. Negative VGS. Okay, so cancel out the VGS as well as the negative. Therefore, what's left? GM RD parallel with RL. Okay, so this is the AV. Okay, all right. Okay, I think that's it. Okay, yeah. All right, so we have derived for the common gate, okay, for the common gate, AC equivalent circuit for all common, okay, we started from the common source and then common drain and then common gate, okay, and then we derived Z in, Z out and AV, okay. Most of the time for MOSFET, they didn't ask you for the current gain because input current usually zero due to the gate. Okay, so for the common for the MOSFET only up to the AV. Okay, AV. All right, I think that's it. Okay, we will continue the example. Okay, this example and also for the common gate example in the next class. All right. Also, in the next class, I will discuss a bit on the test one as well as on the continuation of this derivation. Okay, so do you have any more questions, students? Okay, for those who ask me regarding your test mark, okay, I will reply today, okay, because tomorrow, yesterday was quite busy, really hectic day. I didn't have much time to reply, but I'll try to reply today. All right. If no more question, I think that's it for today. Okay. Student, are you there?
Yes.
Yes.
Madam,
Okay. Yes.
yes. Can get attendance.
Oh. I think I have thank you, Dr. Walker. I have tell like many times, 4th or 5th time. I will not taking attendance from now on because I will only take the attendance from the Webex, my Webex report. Okay, my Webex now I can see the log report where I can see who come in, who didn't come in, and who and what time from what time you join my class. Okay, so from now on, no scanning attendance. Okay. All right. I think that's all. Okay, all. Bye. See you next week. All right. Bye, all.
Thank you.
Okay.
Thank you, sir.
Assalamualaikum. Okay.
Thank you, Tuhan.
Welcome. Welcome.